5X robot arm for 3D manufacturing and automation, fall 2025. Here at UTEP, the College of Engineering. Here are our team members: Sayuriko Miyama, Emilio Ceniceros, me, Walter Puentes, James McDonald, Ramses Baeza, and our professor, Dr. Khan. Why, what, and how? When deciding on what to do for a project, we asked ourselves, how could we improve efficiency in any process? Our first thought was fusion deposition material 3D printing and its print removal process. In most cases, this is done manually. So we decided on designing and building a functional 5 degree of freedom robot arm proof of concept. With this arm and a thermistor, we will monitor the printing process and program the arm to remove material or plate and deposit them at a designated coordinate utilizing inverse kinematics, effectively automizing the most intensive manual part of operating a 3D printer. Bill of materials. In our project, we have 5 degrees of freedom, so we are going to be using 5 motors. 3 45 kilogram per centimeter, those are the gripper, wrist, and elbow. 2 85 kilogram per centimeter, being the shoulder and base. Driving the system is a servo driver connected to our Eligo Uno R3, being powered by a 12 volt 40 amp power supply. We are using a base bearing, wires, screws, and as well as plastic filament for the body, which comes out to a total of $300, which we think is a very competitive price comparing to other hobbyist arms that can lift around the same amount of weight. Program used. We used Arduino C++ to program the robot arm. Prototyping. On the far left, you can see our first try at our inverse kinematics with 3 joints, that being the shoulder, elbow, and wrist. Right now I'm holding it, running the code, seeing how it acts, and it helped us learn a lot for the next picture, which now we incorporate the base and gripper. And already having the 3 joints in the middle, the most important ones, done, made incorporating the base and the gripper much easier. As you can see, we have the circuits on the outside for both these pictures, and on the final design we incorporate them into the base. And on the far right, this is our initial calculation before the arm even existed. We already had an idea of what we wanted it to look like, and so we ran the statics to find out the strength that we needed our motors to be while maintaining a robust factor of safety. Flowchart. So first, you must start a 3D print. And how does your system know that you started a 3D print? That is with a thermistor that will be taped on to a build plate. And once the build plate reaches 100 degrees Fahrenheit, we know the print has started. And then once it goes below 90 degrees Fahrenheit, that is when it's ended. And only then will the arm begin its removal routine. So first, the arm will move to its first coordinate position. Once in position, the gripper will close on the part. Next, the arm moves to the deposit bin, assuming that the removal was successful, of course. And then the print is released from the gripper into the bin. And finally, goes back to home position, waiting for another command. Here's a time lapse of our assembly of the final product. Now here's our final assembly once we've put everything together. As you can see, I'm measuring to the cube the coordinates. The X is from the base to the cube. The height is Z. And I'm also measuring the Y to the deposit bin, and also the Z of the height I would like it to go. And lastly, the X axis for the bin. Okay, then I go to the computer and I input these values into the code as XYZ. Once it's in, I get the soldering iron just for demonstration purposes, and you can't really see it there, but I touch it onto the thermistor, and then after waiting a little bit for it to cool down back to 90 degrees Fahrenheit, it will begin the removal process. Note there is a good amount of jitter and jerking. We will go into more detail on that later in the video. So the gripper moved into position, it closed, and now it moves the cube into the box deposit bin. And that's a success in my book. It moves and it did its purpose, at least as a proof of concept. Here's the second video. That's just a more clear angle of me touching onto the thermistor, the soldering iron. Conclusion and future. In conclusion, we are proud of the advancements we made in completing a functional proof of concept robot arm. We successfully commanded the arm with coordinates utilizing inverse kinematics governed by trigonometry. Nonetheless, there is still work to be done. In future development, we would like to upgrade the body from 3D printed PETG to machined aluminum to reduce deflection. Incorporate PID controllers in all servos to significantly reduce jerking. Create a web app that will allow the user to be notified of the status and facilitate user experience, because as it is right now, it's purely C++ and would take a bit of knowledge to be able to adjust the parameters for everyone's workflow in their workspace. And we will also like to add an extra degree of freedom to the wrist to allow for roll, because right now we only have pitch, and this limits the grip capability. And for an end of arm tooling improvement for the gripper, we would like to add a pressure sensor to know when to stop tightening, as well as silicon tips to improve grip. Acknowledgement and references. We would like to thank the AMAC for granting us access to its training lab to manufacture and assemble our robot. Additionally, we thank Haza for providing materials that supported our progress, as well as thank Dr. Khan for his guidance throughout the project. And here are references, which is ChatGPT to help us generate code, and High Wonder Servos for their documents on how to use their servos within Arduino. And finally, here's our project poster, where we go into further detail on what I've covered in this video, as well as go into an example on how our inverse kinematics works, which mirrors the code. Thank you for watching, and I hope you guys enjoyed. See you.